So this is the internal forced convection. So now the flow is not moving on a sphere or around a cylinder or on a flat plate. This time the flow is going inside a pipe, right? Inside the pipe, inside the duct. So we are trying to calculate the heat transfer as well from the pipe to the fluid, the internal flow, right? So we should expect also HA delta T, right? And the H will come from the Nusselt number, and that Nusselt number should have a relation to the Reynolds and the Prandtl, because again, what is changing the thermal boundary layer? It's the velocity of the fluid, how quickly the flow is moving. That's how quickly the boundary layer will change. So how quickly the flow is moving, that's Reynolds number. And then you multiply by a Prandtl to turn it from momentum boundary layer to thermal boundary layer. All right? One question that was, or one thing that's different this time is that when we are dealing with the flow around a cylinder for external flow in the previous chapter, what is the temperature of the air here? T infinity. Let's assume T infinity. What's the temperature of the air here? T infinity. And here it's T infinity. Everywhere it's T infinity. The air coming to that cylinder, it's T infinity when he's approaching that cylinder. So when you are saying that the Q was H A delta T, you have no question that it was T infinity minus Ts. It's clear that it's T infinity. But when you deal with internal flow, and now the air or the fluid, water or whatever, it's actually moving inside the pipe. He come at T, let's call it T infinity, okay, or T inlet or whatever. But then it leave at completely different temperature. So the air or the fluid, water, kerosene, crude oil, it's not at the same temperature throughout this journey. He's changing his temperature as he's getting heated up or cooled down by the wall. All right? Even more complicated, the Ts might not really be the same. All right? Of course, you could have also said that Ts here could also not be exactly the same, because if the air is cooling it and there is another fluid that's inside, that fluid will change its temperature because of that. So really, in this, in previous chapter, when we were always thinking that Ts is always the same, that was an approximation. So we will solve a problem today where we will track the two of them. We'll track what happened on the inside and what happened at the outside. All right? So I'm just trying to point out that we have to think about what happened to the fluid to the fluid temperature, and therefore properties as he's going through this pipe. Okay? So when we say pipe, we mean circular pipe, and when we talk about ducts, it's basically rectangular ducts or other cross-section areas. So the most famous ducts are, when do we deal with heat transfer from ducts? What's the most famous? It is AC, right? Those are rectangular duct, and they will have heat transfer problem on them. You try to minimize the heat transfer. That's why you put insulation so that the cold air come all the way from the chiller to our classroom without basically heating the attic. Actually, just last week, my wife was asking me, how come every time the air conditioning start, we always get hot air first, and then the cold air? And so I told her, you know the answer. Think, where is the duct coming from? And she said they are in the attic. And I told her, well, how hot is the attic? And she said it's very, very hot, because so obviously the insulation on our ducts are not really good, because, but anyway. So those are the ducts, all right? So one problem with the duct, can you expect any problem that we are going to have dealing with ducts? Anything that's going to complicate our life a little bit when we solve problems?
The turns, it loses a lot of velocity on the turns. It's not as smooth.
So actually the flow go like this, right? So that he doesn't really turn. We assume, for now, we assume infinitely long duct, so don't worry about the corner. No, one thing that will be annoying is it's in both of them. When we solve the heat transfer, we say HA delta T, and the H will be based on the Reynolds and the diameter. What diameter? Well, here this is the diameter. Here, what is the diameter we are going to use in the Reynolds number? Excellent, the hydraulic diameter. So we will have to calculate the hydraulic diameter for those guys so that we can actually find a number that we will use in our Reynolds number. Right? And we should always remember that the velocity we are talking about in those problems, when we say the pipe, the flow come into the pipe with that velocity, this is only the average velocity. In real life, there is not one velocity in this pipe, right? There is a profile. Okay? And why it's zero at both ends, or both sides, or both wall? Because of the no slip boundary condition. The roughness of the surface make the molecule stick. So that's why they have the zero velocity at the wall, and then they have this smooth velocity profile because of the viscosity. Right? And so that's what we are calling V average. That's basically the velocity that will give you the same flow rate in this pipe. All right? And the way to calculate this average velocity is to basically, he's doing an element here, let's say at a distance r from the center line, and then he's basically doing a dr on that, and then he's integrating. So if you know the velocity profile, you can get the average velocity, right? And the same thing for the temperature. If you know a temperature profile, if you can solve for the temperature profile, you can also come up with an average temperature. There will be a temperature profile. The wall is very hot, the fluid is cold, so not everywhere the temperature will be the same. Probably the fluid near the wall will be really hot, and the fluid in the middle will still be cold, right? So that temperature that we say when we say the fluid leave at T exit equals say 40 degree, that T exit is the average velocity. Sorry, the average temperature. It's the average, all right? It's not everywhere the same, it's just the average. And the way to come up with the average temperature is to say that average temperature should have the same energy like all of them. And so he basically divides into slices, and he calculates the temperature, multiply the m dot Cp delta T basically of that small element. So you can see there is rho, there is Cp, and there is, here is the V. So m dot is rho Va, and he multiplied by Cb delta T or Cbt. And that's how you can calculate the energy inside this circular element. And then integrate over the whole thing, and then this way he can calculate the average Tm. Right? So this temperature, right, will also be the average temperature that have the same energy content like the whole cross-section area. Right? So only if you know the temperature profile, then you can do that integration. And in our formulae that we are going to use to calculate the Nusselt number, we will also have two sets. We'll have laminar and turbulent. Just like flow over a flat plate, remember there was like laminar formula and turbulent formula. And why there is a difference? Because turbulence has a lot of mixing. It basically moves the heat transfer more efficiently from the wall. So that's why you should expect two different sets. Huh?
Is H higher in turbulent?
Definitely. And so people who like to increase their heat transfer, they will basically move for turbulent. But people who are worried about their shear stress, and they would like to drop the frictional losses because they don't have this much large pump, they don't want to drive a very large frictional head, they will actually like to make it laminar. Right? So flow over a flat plate, we turned from laminar to turbulent when the Reynolds number was 5 to 10 to the power 5, remember? Based on X. Flow over a pipe, flow in a pipe, the flow will turn from laminar to turbulent when the Reynolds number is above 2,300. So Less than 2,300, the flow is laminar. Higher than this, you go into transition. Some books say 4,000, some book 10,000. Let's stick to our textbook. So our textbook, the flow will become fully turbulent in this pipe above 10,000. So you will, when you solve those problems, flow in a pipe, you calculate the Hughes number. 2,000 and less, you pick the laminar formula. 10,000 higher, you pick the turbulent formula. In the middle, good luck for you.
This doesn't matter what shape the pipe is, right? It could be a square pipe, square pipe.
But the diameter would be the hydraulic diameter. So the JC question is, this 2,300, is it only for circular pipe or for square pipe and rectangular pipe and diamond-shaped pipes? Basically for other ducts, how do you make the transition? So I told him, you calculate the hydraulic diameter for that cross-section area that you have, and from that point on, it's a circular pipe with that new diameter. All right? So here is when he say, to calculate the Hughes number, you need the diameter. And notice that the Hughes number can be written like this, rho Vd over mu, but you can also write it like this. 4 m dot over mu by d. It's the same thing exactly, right? He just lumped the rho and v together. Why this is convenient? Because sometimes you know the m dot and the rho and v, each one of them, you don't really know it. You just know the whole m dot. So rho could change, right? Slightly, because the temperature is going to get higher, the rho will change a little bit, and the v will change with it. But you don't care, you just want to keep your m, you want to know your Hughes number, so you can use the m dot. All right? So sometimes it will be convenient to actually deal with m dot rather than rho and v. All right? And that's when he said the hydraulic diameter. So there are formulas and table for calculating the hydraulic diameter. Of course, for circular pipe, it's hydraulic diameter is the diameter. Right? Of course. For other geometry, why it's A and why it's 2A plus P over A plus P for this guy, that's the formula. It's 4, the hydraulic diameter is 4 cross-section area over the wetted perimeter. Why I'm saying wetted perimeter? Because in case of this, see, if the flow is not covering the whole thing, this is wet, this is wet, this is wet. This is not wet. It doesn't count when you calculate the perimeter. So only the surface which touch the fluid counts. All right? 4 cross-sectional area over the perimeter. So when you do this for all those guys, that's what you'll end up with. D for the pipe. I remember when I was a student, and our books were not, our exam were not open textbook. We were living miserable life when I was a student. Okay, so but we have to invent everything basically in the exam, because we don't even have a cheating sheet. All right? I feel very old when I'm saying this. But so I would usually forget, is it 4AC over P or 4P over AC? That I wouldn't, of course the unit could have helped me, right? But still I would forget. So what I would do is that I remember I always tell myself, let's check by doing the pipe. And if I do it right for the pipe, then I have the right formula. All right? So yes, for a pipe, the hydraulic diameter is the diameter. For a square duct, it's A. For a rectangular duct, it's 2AP over A plus P. And for a channel, wetted channel like this, it's 4AP over 2A plus P, where A is the wetted surface. Right? Amazingly, that hydraulic diameter can calculate not just the Hughes number, right? He can calculate the pressure drop correctly. He can calculate a lot of things. It's like really magic. That's the way to treat a duct. You just get his hydraulic diameter and use it as your length scale. Right? So again, we start at 2,300. That's the end of the laminar, and you are pretty sure it's turbulent after 10,000. And some books say 4,000. 10,000 is easier to remember, I guess. So let's stick to this. All right. So now beside this laminar and turbulent thing, there is also something called the entrance region. All right. So you can imagine at the beginning of the pipe, when the flow is just coming from the well or from the tank or from the whatever the place that this pipe starts, the flow would usually be uniform like this. You know, you are just bringing it from the inlet. And then as we are going into the pipe, eventually you get the wall effect all over the flow. All right? So from this point on, we call it fully developed pipe flow. All right? So how long it takes to do this? That's the entrance length. So the entrance length is basically the distance it takes until the velocity profile basically establishes itself. And I remember when I was a student, graduate student doing my research, we wanted basically to check, we wanted to generate turbulent flow that's pretty well characterized so that we can use it in our experiments. So to make sure that we are really fully developed, we even used a very, very long pipe just to make sure that whatever we are getting at the exit is completely fully developed. There is no question it's fully developed, because if you make it short enough, you are wondering, you know, did the tree establish itself or not yet? But you wait very long, and you are pretty sure it is fully developed, right? Of course, the longer the pipe, the more pressure drop. But I guess it was worth it to actually make sure it is. So there is hydrodynamic entry length, and there is also a thermal. So the temperature, the heat transfer also take a distance in order to establish its temperature profile. All right? And we'll see those numbers in a second. Right? But it's the thermal entrance region will also take time to establish itself, just like the hydrodynamic, just like the fluid mechanics and velocity profile, heat transfer and temperature profile will take time. So which one do you think is better for heat transfer? The entrance region or the fully developed region? Which one will take a lot of heat from our pipe? Say we are trying to cool the pipe by the fluid. Which one is better for heat transfer?
Trying to take heat from the pipe, I'd say the entrance.
Why did you say it? Jesse said this must be really good for the heat transfer.
It's in contact with the barrier rock.
Right, you have very large gradient, right? You have very cold fluid next to the very cold, very hot pipe. So you should expect the edge to do this. As you are going through the pipe, look at the edge. The edge is pretty high at the beginning and then establish itself and drop. Right? And the same thing, of course, for the friction too, for the same reason. Same reason that the shear stress would be higher at the entrance because of the large velocity gradient. You have very large velocity next to the wall, that sheared the wall like crazy. But later on, when the velocity profile just becomes very smooth and you have very small velocity near the wall, the shear stress is reduced. All right? So one should expect two sets of formulas too. One for the entrance region, one for fully developed. All right? So he's basically telling us that to go to turbulent, it's 10 diameter. So that length is almost 10 diameter. So if you have 10 diameter pipe length, you are you are basically over the entrance region, right? So now if the pipe is really, really long, not 10 diameter, but the pipe is like 1,000 diameter, should you really worry about the entrance region or not? So the pipe length is 1,000 diameter. And you have the two formula. The textbook give you the formula for the entrance region, H, and another formula for the fully developed region. Should you worry about the entrance region? Not really, right? Because it's very tiny part of the whole pipe, right? Yes, the heat transfer is stronger over there, but it's only 1/1,000 over the whole thing. Actually, 1/100. It's only 1%. Because we said it's 10 diameter, and we said the pipe is 1,000 diameter. Right. Okay. We will see the formulas in a second. There will be a lot of them. So, before we go there, as we did in that problem, the bunch of cylinders that the flow was going through, the last example we solved, the fluid being heated by the surface eventually end up changing the fluid temperature, right? The fluid will not remain at the same temperature. So if you come at T inlet and you are basically heating the fluid, he would leave at T exit. And the difference between those two guys are such that Q dot over here is M dot CB T exit minus T inlet. And that Q, of course, is from the heat transfer, is HA delta T. All right? So Q is HA delta T. It's also the same Q that you are giving to your fluid, which is M dot CB delta T. Why we haven't seen this before in the external heat transfer? Because we were assuming the TS is like constant like this, and T infinity come over here, and of course it will be heated by this experience, right? And what will leave here is TH, T infinity plus something. But because it was external flow, there was so much air that we didn't really think that that will change the air temperature that much on average. And also because the formula was just based on T film, which is Ts plus T infinity over 2. So we didn't really care about what happened to the air temperature as he moved around the cylinder. But of course it will be heated, right? But if you go behind the tank or behind the cylinder and measure the air temperature, you will not see that much difference because there is so much air, right? Here in internal flow problem, it will make a lot of difference and you will be able to see it, right? Because the air is confined inside this pipe. And so if you increase a little bit, you will be able to see that increase. It will not be dissipated by the other air around the flow, right? So that's why this equation will show up in all our internal flow problems. So on top of QHA delta T, you should always think that fluid inside the duct or inside the pipe will have to increase its energy content. Right? The energy will go into it, and it's HA delta T. Is delta T. Right? So now what Tm? The Q is HA Ts minus Tm. What Tm? What Tm? So that's the mathematical average. And again, that will be accurate only if there is not that much variation between T inlet and T outlet. But if there is big variation between T inlet and T outlet, right? It's not like he changed 1 degree, but you know he came at 75 and or 15 and he leave at 65. When you see this big variation, you have to use the logarithmic mean temperature difference. All right? So that's always more accurate. Actually, if you are in doubt, always use the logarithmic mean temperature difference. The mathematical average will only work if the variation is not that large. Right? And if the Q is over here saying that if the QS is constant, so you are basically giving the flow exactly the same watt per meter square. Every section he goes through, he get exactly the same watt per meter square. How does this happen? Nuclear reaction inside, it's the same, or electric heating, it's the same. So what happened is he's basically telling us that then the TS will actually change with the fluid. As the fluid get heated up going through the pipe, TS also will increase. Because what is constant? QS is constant. So to keep that constant, notice this is HA TS minus T mean. So as this guy go up, TS will also need to go up to maintain the same Q. And so why it was going at different rate here than here? Can anyone explain the difference? This is we are plotting the temperature as function of the distance from the inlet. So this is the temperature of the surface of the pipe.
And it doesn't touch the surface as much anymore whenever the flow changes and it's not touching the surface as much?
So the fluid is always touching the surface. See, the flow is coming from here, coming cold, I guess, at T inlet, and then he leave here at T exit. So this is the temperature of the fluid. And we understand why TS is higher, because QS is leaving the wall into the fluid, so the wall need to be higher than the fluid it's heating. My only question is why the slope is different.
The temperature gradient's bigger in the entrance.
And so
So more convection. Convection happens faster because more new fluid comes in contact with
Right.
the wall faster.
Right. So basically the entrance lens effect, that temperature profile at the inlet, make the H bigger at the inlet, or the heat transfer rate faster at the inlet, and therefore the surface does not get that hot. He can, if the Q is 100 watt per meter square, he can do it with only very small delta T. You make the H smaller and smaller, and delta S or TS need to get higher and higher, so that he can still send the 100 watt per meter square. Okay, so it's the H associated, the higher H associated with the entrance lens that makes something like this, right? So he's basically saying that TS is Tm plus Qs over H. So you make H smaller, and TS will have to get higher, right? You make Tm higher because he's getting hotter and hotter. TS also will get hotter and hotter. Okay? I guess here he's going to prove to us that I guess the Q is why the slope is constant at the end. Let's skip this part. Right. Here when he's talk about the temperature difference. So that Q is HA TS minus Tm. That Tm is the average temperature between T inlet and T exit. And that's the mathematical average, and that's only going to work if T inlet and T exit is is close to each other. And he said, well, we need a better way to calculate it, the average, and therefore the better way is the logarithmic mean temperature difference, right? And that's he's trying to prove what is the logarithmic mean temperature difference, and so that's the proof, and that is the expression for the logarithmic mean temperature difference. And it doesn't matter whether we start with delta T at the exit or delta T at the inlet, as we said earlier today. Right? Let's skip this. We will actually go to this number of transfer unit when we go to the heat exchanger later on. Alright, so now he will basically show us the formula for laminar flow in cubes. So laminar flow, we can get that velocity profile exactly by solving the Navier-Stokes equation. So they don't need experiments for that. They can solve this analytically using just the equations. Okay, and so they are trying to calculate the velocity, and so they, just like what we did with the temperature, they start with, this is cold, this is kind of the Navier-Stokes equation for this particular geometry. When you have circular pipe, the flow is laminar, you know the velocity is moving a little bit slowly, so because it's laminar flow, then this is the equation. And to come up with the velocity profile out of this, look, it's double integration for the U. The U is the velocity. And the delta B over delta X, that's the pressure drop driving the flow. The flow is moving into the pipe because there is a pressure difference. Because the pressure at the front is higher than the pressure at the end. That pressure difference is what's eating or what's compensating for the shear stress, for the friction at the wall. That's why the flow ends up moving. And the faster the flow, the more the frictional losses, the more the pressure gradient needed to actually drive it, right? So you increase the pressure and the flow will end up moving faster, right? So he integrated twice, he came up with the concept from the boundary condition, and then he came up with the velocity profile. This is the velocity profile in the pipe, and so he can actually plot that velocity profile. And then if he would like to get the average velocity in this thing, then he can actually integrate this velocity profile and come up with that. And so he did. And so this is the average velocity. And Vmax here, and in the middle, of course, is twice the average velocity. Or basically the average velocity is half the Vmax. Alright? So what I'm trying to say is that the velocity profile for a laminar flow is, you can obtain this analytically actually, as well as the shear stress at the wall. And if you remember a Moody chart from your fluid course, it was something like this. And for laminar flow, there was only one correlation for the whole, or one equation for the whole thing. That equation came from solving Navier-Stokes equation. Right? So when we say the F for laminar flow is 64 over the Reynolds, this equation, or this particular only line here, for any pipe, any cross section, any diameter, any fluid, it's all F is always 64 over the Reynolds number. It came from solving that equation. Right? And if you know V average, then you can calculate M dot or V dot, the volume per unit second, meter cube per second, and then you can actually correlate that flow rate to the delta B. So that's really convenient. So if you know the delta B on the pipe, you can tell what's the average velocity and also what is the flow rate. Of course, because the flow rate is the average velocity multiplied by the cross-section area. But what this is convenient so is that you would probably need the Reynolds number in those problems to calculate the Nusselt number, to calculate the H, to calculate the Q. And so the Reynolds number requires the velocity, and the velocity can come up directly from the pressure drop in the pipe. So if I can give you the pressure drop and the geometry of the pipe, I'll tell you what is the heat transfer. So you will drive it from this. Knowing the pressure drop, you can tell the velocity, and therefore you can get the Reynolds number. Right? They can do the same thing with temperature, just like what they did with the velocity. We can also try to calculate the velocity, the temperature profile on the pipe. Right? So this is just the energy equation, and so they end up with it like this, and then they integrate this, putting the boundary condition. That's the temperature profile. They can plot this, and they can calculate the H out of it as well. Right? So that H for a circular pipe is not experimental. This is an analytical solution. So it's kind of like really accurate. Right? And so for a constant surface pipe, the Nusselt number is simply 3.66. Right? So all you need is to multiply the 3.66 times K over D, and you will get your H. It cannot be easier than this. So laminar flow in a pipe, Nusselt number is simply 3.66. Where did this come from? You can just follow those 5 pages that we had before, and you'll see how did they drive it. Right? What if it's not circular pipe, it's rectangular duct, square duct, same thing, but use the hydraulic diameter. Jameson.
Did you say 3.66?
3.66. This guy, whatever is written here, that is the Nusselt number. Right? And so this is for a pipe with diameter D. For anything else, you just calculate the hydraulic diameter from 4 cross-sectional area over the weighted perimeter. Right? So this was actually to to come up with this, to come up with that temperature profile, they have TS. TS was given. TS was constant. Right? So now, for TS to be constant, that's not always the case. TS can be constant if we are talking about the pipe in a condensers. You know, a power plant where the steam is condensing. Yes, the steam will condense at, say, 100 degrees C. And while the cooling water inside will basically change its temperature. So that's a case for TS constant, when the other fluid is changing phase. He will maintain the TS constant. But in other scenario, TS is not constant. What constant is QS. The pipe receive a certain QS, certain flux. We don't know TS. So if this is the case, still laminar pipe. But it's not TS, it's QS. So if QS is constant, rather than 3.66 for constant TS, it's 4.36 for constant QS. Right? So you will end up with this table basically for laminar flow. And what is a laminar flow? Reynolds number less than 2,300. So you just basically check your formula or your table, find out what is the cross-sectional area, and is it constant S or constant TS or constant QS? Is the temperature is constant or the flux is constant? And you pick the Nusselt number to use. All right. So why does the A and B change the coefficient? Look at this. The rectangular duct with A and B, one, that's a square. That's a rectangle. That's a very large rectangle. And you can see that the constant, the Nusselt number, and note that the Nusselt number has the diameter into it, and the diameter is the hydraulic diameter. So the A and B itself, it's already there in the hydraulic diameter, but still the coefficient is different, or basically the heat transfer is different from this to this. Why?
Because the pressure is higher on the bottom of the tall rectangle.
Say that again.
The pressure is higher on the bottom of the tall rectangle.
No, let's assume air. So I'm really thinking that, well, if this is water, probably the hydrostatic will build up here. So the pressure at the bottom will be really higher than the top. For water, yeah, maybe. But not for air, right? For air, let's assume the whole thing is just one, it's almost one pressure, right? At every cross-section area, it's just one pressure.
For natural convection?
Huh?
Natural convection, heat rises, so it would be hotter at the top of the
I think
That, Jesse actually have a good point. So Jesse said it's maybe because natural convection will actually do something into it. That actually could be a good reason. But
the thinner,
but the temperature need to be really big to actually to do something important. What else you think?
the larger the ratio of A over B, the thinner the duct will be.
Right.
And thus more air will be adjacent to the wall of the duct, and convection will be faster.
It's probably so. James is
Please.
Jason. Sorry, Jason. So James actually was pointing me to if no, he's not James. Yes. So the profile will be really different, right? If the duct is very, very thin, right, it will not be like an actual pipe anymore. So that constant that we had for a pipe will basically get screwed up, right? So the geometry really play a role in this. Whether natural convection is doing something or not, I think it has to do with how large is that B and whether the temperature that's driving natural convection is really very strong. Usually forced convection is order of magnitude higher than natural convection. Natural convection is really very, very small compared to it. So it's like 101 or 102. It's not that big a deal. Later on, actually in the course, when we go to natural convection, we will see how we decide whether natural convection can be counted in or should we completely neglect it. So there is a ratio between two numbers that will basically tell us that, you know, it's 10%, you cannot neglect this thing, or is it, it's 1%. Go ahead and neglect this, it's not a big deal. James.
So why does it matter if it's a sideways rectangle or a vertical rectangle?
So we didn't actually say the other side. So you're thinking, why did they don't have the 0.5 and 2 to show us the difference? So that's another proof that maybe natural convection is not really the reason. Because 2, there's just the 2, there's no 0.5. It doesn't really matter whether it's on its base or it's in its width. So it's not natural convection. It's basically because of the flow geometry in such a small, in such new geometry now. Right? Whether the flow would be the same or not.
I mean, how does the air know that it's a vertical rectangle or horizontal?
So that would be the pressure, but he doesn't. The air does not. So basically, the pressure here in this room is 1 bar, right? It's 100,000 K. Why the pressure here is 100,000 K?
Because we're under so much air.
We under rho GH air. We are under 10, almost 10 kilometer air with density of 1 with a gravity of 10. It's the weight of the air we are carrying on top of our head. So we have 10 kilometer of air on top of, almost 10 kilometer of air on top of our head with gravity equal 10, almost, it's 9.81, time density equal 1. It's not, it's 1.2, but then it gets smaller. But at the end of the day, you carry 100,000 on top of your head, right? So now, this Coke here, what would be the pressure here? At the bottom of the Coke, let me open it. So 1 bar here, right? And here it's 1 bar plus hydrostatic pressure, rho, which is 1,000 now. It's not 1 anymore. So rho here is 1,000 because it's water. 1,000 multiplied by G multiplied by the 10 centimeter. Right? So 1,000 multiplied by 10 multiplied by 0.1. So that's already 1,000 Pascal. So if the pressure here is 100 kilopascal, it's actually 101 kilopascal. Here it's 102 kilopascal. Right? So if this duct that we are looking at over here is 10 centimeters, the pressure from the top to the bottom would be 1,000 Pascal higher, just for 10 centimeters of water. 1,000 Pascal. Well, will what, this 1,000 make a difference? If it's already 101, will it be 102? Well, maybe 1 is not really a big deal, but if the pressure is already lower, they are under vacuum or something. So that one, but anyway, that hydrostatic pressure is not doing anything. And that's why they didn't put the duct vertical or rectangular. They didn't tell you A over B is 2 or 0.5. It's not doing anything because the difference is small.
But still, why do you have those different result numbers for different A and B?
So those are for different channel geometry. So if it's like a slat, it's moving from a square to a rectangle. Correct. Correct.
1/1, it's A and B are the same.
So 1 over B is 1 is basically a square. And 1 over B equal infinity. That's a slat. It's a flow between two plates. Right? You are moving the two walls farther and farther away. Right? Actually, I remember when I was a master student, it wasn't my thesis, but one of the students in our lab was basically studying the flow between, the heat transfer between two cylinders like this. And how will it improve if we actually add 4 divider like this? And it did improve. The heat transfer really improved with this. And it's not because you give it more area. It's not like here we have more walls. It's because that corners create, and this is really advanced. You don't really need to listen to this if it's confusing you. But basically, rather than the flow just moving like this, between the two pipes, those corners create a small circulation that basically improve the mixing. And that's why when I went to Michigan for my PhD, the wind tunnel they have a very big wind tunnel. It's actually, the cross-section area is 5 by 5 feet. In my first day over there, my professor insisted on taking me to the wind tunnel to show it to me, and he asked me to go inside the test section instead. I didn't want to go inside the test section, you know, not that he's going to turn it on me or anything, but he insisted, let's go in. He just wanted to show me that we can actually fit inside the test section. And he was a football guy, and when he was young, he played football, so he was really much taller than me. And still, of course, he was bending to fit in, and I was standing next to him inside the wind tunnel to see it. And when I was there, it's really big wind tunnel. The cross-section area only is 5 by 5. And the cross-section area was like this. So it's not complete square. They cut the corners from it because they don't want those things to basically, those eddies to generate and mess with their flow. They want their flow to be uniform inside the wind tunnel. All right? So what do we learn from all this thing? That the geometry really affect the heat transfer, and we have to make sure that when we are picking the formula from our table, it really fit the problem. Right? So a square is not the same as a rectangle. Right? So make sure you pick the right line for the edge. Right? So what was the flow for pipe? What was the Nusselt number for a pipe flow? Laminar pipe flow? 3.66, right? Look at this. Now you get this extra Nusselt number, extra heat transfer from the entrance region. Right? So this basically 0.565 D over L, Reynolds, Prandtl over all the stuff. This get basically extra boost to the Nusselt number. What if D over L is 0? Why D over L is 0? When D over L will be 0?
It's really long.
When it's very, very long. So you know, like the gas pipeline coming or the oil pipeline coming from Canada to the Gulf of Mexico. Should we really care about the D over L boost? It's almost 0, right? So this formula would, when you think about it, it will really work always, whether you have entrance lengths or not, because if the pipeline is really very big, this formula will correct itself, and will just make this correction go to become very tiny, that you don't have to worry about it. Okay? Very good. And so this correct our 3.66, that's the magic number for laminar flow in a pipe. This formula corrected for entrance lengths, and the other formula here correct this for the, I cannot get my, okay. This formula over here corrected for large TS. So if the TS is really, really large, now the thermal boundary layer property would be really, will be different from the bulk temperature. You think that in those formulas we think the fluid is sitting at its average temperature. He's coming at T inlet 50 degrees, he's leaving at 90. But if TS is really hot, TS is very large, the temperature profile could actually be something like this. So the average will not really represent what happened in the boundary layer. The average temperature at that cross-section area will not really be, this temperature is not a good representation of what happened in the thermal boundary layer between the wall and the fluid sitting next to it. So this will happen when the temperature at the wall is really, really hot. So that's why you need that correction or that formula. So this formula will be more accurate to use when nu S is really large or TS is really different from T bulk. Right? And again, all properties are evaluated at the bulk mean fluid temperature except for mu s, which is evaluated at the surface temperature. All right? And this is the formula for isothermal parallel plates of length L. So this is isothermal parallel plates. Look at this. Flow in a duct, as the aspect ratio become really big and it's not square anymore. It's really a flow between two plates really at the extreme. It's 7.54. Right? So that's what you see, 7.54. Right? 7.54 plus, of course, the correction from the entrance length. Why it's less than 2,800? This formula is valid when the unit number is less than 2,800. Why is that? Just laminar, excellent. Eric, correct? So just laminar, because after that the flow become turbulent. So now what happened in turbulent flow? Things become very chaotic. There is huge mixing. All right? This is actually again, it's the same physics. Reynolds multiplied by a Prandtl, but the power would be different, the coefficient will be different. All right? Because you get not just layers sliding against each other, but you get this extra mixing. All right? So this formula is valid for news greater than 10,000 because you want to make sure he's turbulent. So it's greater than 10,000. And if you notice, it's Prandtl to 1/3. So it's this is called Colburn equation. Those two guys, Litz and Butler, said, no, let's actually keep it just power n, not 1/3, not 0.3. Let's keep it one power n, and this n would be 0.4 for heating and 0.3 for cooling. Right? And this is what we are going to solve next time. So we will actually use the turbulent formula, and we will determine the power based on are we heating or cooling. All right? And let me finish by this one. So this is the same, but you have correction for, again, very large TS. If the surface temperature is very far away from or very different from the fluid, you have to fix for what is the new thermal boundary condition temperature. And this is what those formulas are working for. All right? Thank you.